We're taking a look at what is arguably one of the biggest, most closely guarded secrets in the entire AI industry right now. Look, if you've been following the massive explosion in AI, you've definitely heard of models boasting hundreds of billions or literally trillions of parameters. But here's the wild part. How on earth do these massive models actually run without instantly melting down the world's data centers? Well, the secret sauce is an incredibly elegant architecture called the mixture of experts, also known as the architecture of sparse intelligence.
So, what if I told you that some of the most powerful AI models on the planet don't actually use their full brain? It's true. When you prompt them, they actually power down the vast majority of their neural connections. Not every neuron fires, not every parameter gets used. Instead, they only wake up the exact specific specialist they need for that precise moment. It's such a fascinating concept, and honestly, this single idea is the main reason these trillion-parameter titans can even exist in the real world. Section 1. The giant compute problem. Okay, so to really grasp this, we first need to understand the absolute wall engineers hit before this architecture was introduced. Modern models are scaling up fast, billions, hundreds of billions, racing toward trillions of parameters. And just as a quick refresher, parameters are essentially the learned knowledge patterns inside an AI model. But here's the issue. Storing and running that many parameters requires an unbelievable amount of physical space and pure processing juice. We're talking GPU temperature spiking, electric meters spinning out of control, and it all stems from how traditional models operate. In a classic dense model, absolutely every single layer, every single parameter turns on for every single task. That means even if you give it a ridiculously simple prompt like translate hello to French, it forces the entire massive network to fire up. Think of it like a huge corporation. Imagine walking into the lobby and yelling, "What's 2 plus 2?" And suddenly every single employee, the engineers, the HR department, the lawyers, drops everything they're doing to solve it. It's just a massive, massive compute waste. Thousands of workers running around chaotically for one basic task.
Section 2. The mixture of experts.
So, how do we fix this huge inefficiency? Well, the answer is selective intelligence. Instead of making the entire company do the math problem, you just call the specific specialists you need. So rather than relying on one giant, overworked generalist brain trying to do absolutely everything, the mixture of experts architecture creates a bunch of smaller, highly specialized expert brains within the larger system. You might have one expert dedicated entirely to math, another for language translation, one for coding, and so on. For every single word or token the system processes, it actively decides exactly who needs to think, and the rest of the experts, they just stay completely asleep.
Section 3. How the router works.
So how does the AI actually know who to wake up? That is where this brilliant little mechanism called the router comes in, and the pipeline is actually surprisingly straightforward. Step 1. An input token arrives, say you type explain black holes. Step 2. That input hits the router, which is sometimes called a gating network. The router's job is super fast and super simple. It basically asks, okay, which experts are best equipped to handle this specific token? It quickly scans the available specialists. Then, step 3, top K routing. The router activates only the top few experts perfectly suited for the job. So maybe just the physics expert and the reasoning expert light up, while everyone else stays completely dark.
Now, what's genuinely mind-blowing here is the math. Let's take the number 2. Out of, say, 128 total experts sitting inside the AI, the router might only activate 2 of them for any given word. This is what we call sparse activation. So even if the AI has this totally massive pool of intelligence and hundreds of billions of parameters, only a tiny, tiny fraction is actively doing work at any given second. The compute power drops dramatically. Electricity usage absolutely plummets, and yet the intelligence output stays incredibly high.
Section 4. Massive scale, lower power.
When we zoom out to the macro level, the real magic of this becomes clear. You get bigger intelligence with much lower active compute. Because of this sparse activation, you can scale AI models to be massively larger, without the active computation blowing up at the same rate. We're no longer relying on one stressed-out generalist juggling all human knowledge. It's way more like owning a sprawling, futuristic city of specialists. You've got a dedicated math district, a code district, a language district, and that specialization really matters. A coding expert can become incredibly sharp at its job, without its parameters ever getting tangled up with the language expert's parameters.
And hey, this isn't just theory. Right now, today, many of the most advanced AI systems on Earth rely on MoE architectures. We're talking heavy hitters like Mixtral, Google's Switch Transformer, Gemini, and DeepSeek. Some of these incredibly powerful systems have completely mind-bending parameter counts, yet they achieve these lightning-fast speeds specifically because they're only lighting up a fraction of their brains during inference. It's honestly a huge part of why modern AI scaling has exploded so fast over the last couple of years.
Section 5. The hidden traffic jams.
But, of course, there's always a catch, right? Building a mixture of expert setup comes with some incredibly complex engineering headaches and huge potential bottlenecks. First up, you have to watch out for expert collapse. Imagine if literally everyone keeps asking the AI to write Python code. The coding expert gets absolutely swamped with requests, while the poetry expert is just sitting there twiddling its thumbs. This creates a massive load imbalance, so engineers have to carefully manage the traffic so no single expert collapses under the weight. The second big issue is synchronization overhead. Because these different experts are so massive, they often live on entirely different physical GPUs inside a server rack. Moving all that data back and forth between different physical chips, it is not easy. Coordinating all these specialists in real time is like conducting an incredibly complex, high-speed ballet of data.
Section 6. A society of specialists.
Yet, despite all those engineering hurdles, a lot of researchers truly believe this represents the grand future of artificial intelligence. We're moving away from the old idea of one giant monolithic brain and moving toward modular intelligence. We are talking about planetary-scale AI systems containing not just tens or hundreds, but millions of expert nodes that dynamically activate and reorganize in real time. Picture a whole civilization of specialists, where medical experts dynamically consult with physics experts, or creative nodes check in with logical reasoning nodes, all evolving together like a massive digital ecosystem. Which brings us to our final thought for this explainer. Is AI fundamentally transforming from one giant brute force worker into a highly efficient, intelligent society of specialists? Mixture of experts allows for massive scaling without all that massive wasteful computation. It is the secret architecture that made today's AI boom possible, and the wild part is, we might only be seeing the very beginning of what this modular approach can achieve. Thanks so much for joining me to unpack this fascinating architecture. And as always, keep questioning how the amazing tech around you actually works.